speaker is Qingyu Zhu, and he received his Bachelor of Science in Geophysics from the University of Science and Technology of China in 2015, and then did his PhD in physics at the University of Texas at Arlington, where he graduated in August 2020. And then he worked until the end of 2020 as a postdoc there at UT Arlington. And then in January 2021, Qingyu started his postdoc here at NCAR through the Advanced Study Program working at in HAO. And he has been studying the ionosphere electrodynamics, especially at high latitudes. And during his PhD, he worked actively on analyzing satellite-based measurements, including ion drift and electron precipitation measurements from low Earth orbit satellites. And he also has a lot of experience with numerical simulations, including developing high-latitude empirical models and working with the global ionosphere thermosphere model. And today he will talk about improving Joule heating estimations in general circulation models. So please go ahead.
Okay, thank you for the introduction, Nick. So hello everyone. So this is Qingyu. So I'm a new postdoc at HAO. And today I'm going to talk about improving Joule heating estimations in general circulation models. And most of the content come from my dissertation work. So before going further, I would like to thank for the contributions from my dissertation advisor, Yue, and along with Astrid, Art, Dolores, as other courses from the CU and UT Dallas. So although I'm a new staff for the HAO, so it seems that I have some connections with people from HAO even before starting my graduate school. So my undergraduate and graduate thesis advisors are were both postdocs when roughly about 15 years ago, and I also came here every summer for the summer visitings with Astrid and Art. So the summer visitings not only facilitate my collaborations with them, but also offer me an opportunity to escape the hot summers from the Texas. So for today's presentation, I would like to first start with a short introduction. And after that, I'm going to talk about how to improve the Joule heating estimations in GCMs from two aspects, the variabilities and the soft electron precipitations. So the first one mainly focuses on the especially small and mesoscale. So and the next one primarily focuses on the large scale. So, and after that, I'll briefly introduce some ongoing projects, and then as the last part is a summary of today's presentation. So the region we are going to focus on today is the upper part of the atmosphere, the thermosphere, where the neutral temperatures undergoes a significant enhancement due to the absorption of the extreme ultraviolet radiations. So the UV radiations not only heat up the thermos, but also ionize the neutrals, leading to the formations of the ionosphere. So the major part of the ionosphere, so-called E region and F regions, are mostly co-located with the thermosphere. So the coupling between the ionosphere and thermosphere can be very significant. So owing to the existence of the ionized particles, the existence of the electric field in the ionosphere, in the upper atmosphere is a very important factors for the need to be taken into account for the upper atmosphere. So the ionospheric electric field mainly comes from two sources. The first one is the internal wind dynamo. This is due to the neutral wind flowing across the magnetic field line, and such process is extremely important for the low and middle latitude regions. And the other part and the other source of the ionospheric electric field, which will be mostly focused on today, is come from the coupling between the solar wind and the magnetosphere. The electric field generated in the magnetosphere can map down along the field line to the ionospheric, driving the convection of the ionosphere ions. And the coupling between the solar wind magnetosphere and magnetosphere not only generate the electric field, but also lead to the precipitations of energetic particles. So especially for the upper atmosphere, the electron precipitation is more important. And the most energetic electrons are precipitated to a RINAC region called aurora zone. And the particle precipitation is also an important ionization source for the high altitude upper atmosphere. And the impact of the energetic particles to the upper atmosphere depend on their energies. So high energies can precipitate to low altitude and thus cause more effect on the lower altitude, and the opposite is true for the relatively low energy electrons. So the heating will generate as the current flow in a weak conductance, and which is called Joule heating. If we view from a big picture, the Joule heating is actually a conversion of the electromagnetic energy carried by the field line current. So the Joule heating is a conversion of the electromagnetic energy carried by the field line currents. So the heating can be expressed as a combination of the ionospheric conductivity, the electric field, the neutral wind flow in the thermosphere, and the geomagnetic field. So in terms of their height profile, so the Joule heating roughly peaks at the altitude between 110 and 112, where the Peterson conductivity peaks, and the Joule heating decreases significantly as the altitude increases. And in terms of its horizontal distributions, here we focus on the height integrate Joule heating. So the Joule heating, the distribution of Joule heating significantly depends on the directions of the interplanetary magnetic field. And you can see there are two peaks when the interplanetary, the IMF is southward. And for the contributions of the neutrons, it sometimes can be non-negligible at certain locations. For example, as you can see, there could be large discrepancies between the red line, where the neutral wind is taken into account in the calculations, and the black line, where the neutral wind is not taken into account in the calculations. So the Joule heating can be huge during geomagnetic storms, and can be dominant when during the super geomagnetic storms. So Joule heating can also, such large Joule heating can also significantly affect the ionosphere and thermosphere during the geomagnetic storms. For example, the neutral temperature and the neutral density could increase dramatically due to the enhanced Joule heating, and causing some challenges in satellite tracking. So the impact of Joule heating on neutral density will be focused later on. And also, the Joule heating could also significantly change the thermosphere neutral compositions as well as the electrodynamics, so that the ionosphere could also be modified accordingly. Furthermore, the traveling atmospheric disturbances and also as well the traveling ionosphere disturbances can also be excited during the geomagnetic storms. So to better understand the distribution of the geoheating and its consequence, the general circulation models are widely used. However, it's still challenging to accurately estimate the geoheating in GCMs. And the part of the difficulties lies into the specifications of the particle precipitation as well as the ionospheric electric field. So those two components are typically specified by the imperial model that can capture their climatological distributions under certain conditions. However, due to the dynamic natures of those two items, well, it's the deficiencies of existing imperial models may lead to inaccurate geoheating estimations, and that may contribute to the inaccuracies of the estimating the ionosphere and thermosphere quantities, such as the neutral mass density, temperature, compositions, and also the ionospheric peak density, so on. So for the deficiency of the current imperial models, the first one I'm going to talk is the variabilities that cannot be well captured by most imperial models, since the imperial models are aimed to capture the average of those the quantities. For example, for the if we try to calculate the mean of the geoheating, besides the average of the electric field, the electric field variability or the variance of the electric field is also important for the calculating the average of geoheating. Here we assume that the Peterson conductivity and the electric field are independent, and also the contribution of the neutral wind is ignored for the purpose of illustrations. So the electric field variability is actually comparable with the mean electric field. So the geoheating can be significantly underestimated if the electric field variability is not well quantified. But here we assume that the conductivity and the electric field are independent. But how can things change if they are not independent? So this will be the first topic we were going to focus on in this presentation. And for the deficiency, another deficiency that might affect the geoheating estimation is the soft electron precipitations. So it seems that for the storm time F region neutral density variations, the geoheating deposit in the F region can more efficiently enhance the neutral density than the geoheating deposit into the E region. Although the total magnitude of the geoheating deposit in the F region is much smaller than those deposited in the E region. So here, what you can see here are two experiments. One experiment, the F region geoheating is not turned off, and this bottom one shows the experiment where the F region geoheating is turned off. So as you can see, when the F region geoheating is turned off, the neutral density enhancement at the in the altitudinal region where no Earth orbit satellite flies is actually much lower than the F region geoheating is not turned off. And for the F region geoheating, if we just ignore the inaccuracies in the electric field specifications, the specifications of the ionospheric conductivity may also cause the underestimation or the inaccuracies of the F region geoheating. This is because that the F region conductivity is very sensitive to the soft electron precipitation, which carries the energy smaller than 1 keV. So, but sometimes, in most existing impure models, we tend to use some assumptions on the energy spectrum, such as the Maxwellian spectrum. So even we correctly estimate the keV particles, there could be very large discrepancies for the soft electrons. So can we could the improvement in the soft electron precipitations also help to improve the specifications of Joule heating? So this will be the second topic of this presentation. So with those questions in mind, let's proceed to the result part. So first, let's focus on the variability part. So previously, we assume in the illustration, we assume that the conductivity is independent with the electric field. However, the previous studies suggest that there could be anti-correlations between the electric field and the electron precipitations, especially on small scales. So here, by mean small scales, we mean the scales below 500 kilometers. So if such anti-correlation is universal but is ignored, there could be very large overestimations of Joule heating. So, but the question is, to date, the correlations between the electric field and electron precipitations are not well understood. So it's not well established how they are correlated on at different locations and on different scales. So therefore, it's not well understood how the correlation could affect the Joule heating estimations in GCMs. So to address those questions, so we first we have analyzed the electron precipitation and electric field data from the D2 satellites. And we have statistically analyzed them and using those statistical information to drive the global ionosphere surface wave model to investigate to what extent the correlation between the electric field and electron precipitation can contribute to the Joule heating. So here is some notes for the GIDM, the global ionosphere thermosphere model. So which is a GCM for the upper atmosphere. Like most GCMs, it solves for the density, velocity, and temperature and of the neutrons, ions, and electrons by solving the continuity equation, momentum equation, and energy equation. So it relaxes some assumptions used in other GCMs. So it may be more computational expensive than other GCMs. So, and it also has very flexible grid resolutions. So, and with the data and model in mind, let's proceed to the result part. So here shows how we identify the large and small scales in the electric field and electron precipitations. So basically, we apply a 500 kilometer sliding window to obtain the large scales and assume the residuals with respect to the large scale value is the small scale quantity. So, and then we bin the data and calculate the average and standard deviations of each quantities. So here you can see the distributions of the electric field magnitude and the total energy flux on large and small scales. So for the large scales, the averages is generally larger than the standard deviations, while the except for the total energy flux on the premium line, where the standard deviations is larger than the averages. And for the small scales, the averages are generally small, while the standard deviations are much larger. So, and then we calculate the correlations between the electric field and the electron precipitations on different scales. And so, we first calculate each beam, and then we combine all beams together. We can get the distributions of the correlations. So basically, for the large scale, there are the positive and the positive correlation and anti-correlations. Both of them exist. For the positive correlations, they mostly in the post-midnight and morning side, and also below 60 degrees. However, and there are also some anti-correlations, mostly in the premium light. However, for the small scale, you can see that the anti-correlations almost occur everywhere except for certain regions. And such anti-correlations may suggest that the magnetosphere tend to be a current generators on small scale. So next, we have the statistical result in hand. We can further investigate the impact of the small scale variabilities. Here we specifically focus on small scale variabilities because it's, as you can see, it's generally an anti-correlation. It's a general, so the anti-correlation generally occur everywhere. So for the impact of the small scale variability, first you can see how the small scale electric field variability in fact will affect the calculation of jaw heating. So here, as you can see, on the left, it's a pattern where the small scale electric field variability is not taken into account. And on the right, we added only the small scale electric field variability, but not the small scale, but we exclude the small scale particle precipitations. So as you can see, after including the small scale electric field variability, the total jaw heating increases by roughly about 30%, which is not negligible. And then we further include the small scale electric field electron precipitation variability according to the correlation between the electric field variability. So on the left, it shows basically the result from round 2, where only the small scale electric field variability is included. And in the middle, we show that the result from where the both small scale electric field variability and small scale precipitation variability are excluded. And on the right, we show the percent differences between round 2 and round 3. So overall, we see that by including the small scale electron precipitation variability, the hemispheric integrated jaw heating decreases roughly by 5%. And more importantly, the localized reduction can be up to 75%, which is not negligible, especially on the dark side. So here is the summary for the first part. So we have investigated the correlation between the electric field and electron precipitation and high altitude. So we found that on small scales, the electric field is generally anti-correlated with the electron precipitations. And then we further investigate the small scale, how the correlations between the small scale and electron precipitation variabilities will impact the jaw heating calculations. And we found that although the small scale electric field tend to lead to a significant enhancement in jaw heating, any correlations between the small-scale electric field and electric precipitation would result in the reductions in Joule heating, especially the localized reductions on the dark side is not negligible. So after the result about how the Joule heating can be affected by the variability, let's focus on another part, is that how the soft electron precipitations would affect the Joule heating estimations and as well as the estimations of the neutral density enhancement during the storm time. So as mentioned earlier, the typically used Maxwellian spectrum given by the total energy flux and average energy provided by the improved models significantly underestimate the soft electron precipitations as compared with the observations. So, and sometimes the underestimations can reach 2 or 3 orders of magnitude. So there are some efforts to include the electron precipitations in the models. So this is earlier simulations led by Bingzhen. So indeed, once these soft electron precipitations are included in the models, there are non-negligible enhancement in the vicinity where the soft electron precipitations is added. However, as you can see, those soft electron precipitations only added in the limit regions and also only included only a certain types of sources. However, the sources for the soft electron precipitations is actually more complicated. So in addition to the direct precipitations, the reflections at the top of the ionosphere, as well as the precipitation from the conjugate hemisphere, will also contribute to the observed soft electron precipitation at the DMSP altitudes. So it's not well established how the soft electron precipitation how does the soft electron precipitation distribute in the horizon under different geomagnetic conditions, which will be important for the investigation the impact of soft electron precipitations on the thermosphere during geomagnetic storms. So to address current limitations of the knowledge on the soft electron precipitations, we have developed empirical models that can better specify soft electron precipitations in the horizon. So the electron precipitation model is called HAO, which is one component of the recently developed HAO model. The HAO stands for the Auroral Energy Spectrum and High Altitude Electric Field Variability. So the HAO is based on the electron precipitation measurements, specifically the SSJ5 on both the DMSP F16 to 18 satellite during 2010 and 2015. So the SSJ measures the incident electrons and the ions in 19 energy channels from 30 eV to 30 keV. And based on those differential energy fluxes, the total energy flux and characteristic energy can be calculated. And that's the most empirical models will work on. However, for the HAO model, instead of modeling the total energy flux and the characteristic energy, so HAO directly models the differential energy fluxes in the 90 energy channels. So it can reflect the distributions in each channels, as you can see on the next slide. So here, what you can see on the right is the distributions of the differential energy flux in 90 energy channels for it's moderate strong southward IMF conditions. So by the way, all the component of Ashley is driven by the IMF BZ, BY, and the solar wind velocity and the solar wind density. So here you can see the distributions in the top two rows are quite different from the distributions in the bottom two rows. So the top two rows mostly shows the distributions of energy flux, differential energy flux in the KeV range, where you can see the most electron precipitations in the KeV range tend to precipitate on the night side. However, for the soft electron part, especially for the 100 to 200 eV range, the precipitation are more likely to precipitate on the day side. So especially for the channels around 100 eV, there is a dominant peak near the day side, which in the day side at noon, which might correspond to the location of the day side cusp. So on the bottom left, we show what's the differences between the spectrum from HLA and the Maxwellian spectrum using the total energy flux and the characteristic energy of HLA spectrum. So as you can see, there could be the differences between the 100 eV particles can be two orders. So which is sort of consistent with the results shown in the previous comparisons with observations.
Can I ask, Qingyu, could I ask a question about that last plot before you leave it? Right, so you have these solar wind conditions indicated at the top. How are these distributions being generated or calculated? Is this from data? Is this from a simulation?
Yeah, right. This is actually from the data. We first bin the data for certain types of conditions, and we calculate the averages. So this actually shows. Well, this is already the model output, but we bin the data and calculate the averages, and then we just do some fittings to collect different categories.
Okay, so for those IMF conditions, the solar wind interplanetary magnetic field's never going to give exactly IMF BZ minus 8 nanotesla BY equals 0. I mean, there will be times that occurs, but so there's some angular spread about the clock angle so this is due south, but it's not exactly due south, right?
Right, yeah. Yeah, we bin the data maybe each 45-degree clock angles. For the nanotesla, for this maybe every two nanotesla in terms of the IMF magnitude. So that's one thing. So yeah, we have generated a lot of patterns, and then we feed the data, do some Fourier fittings, and do some interpolations.
Okay, thank you. Onward.
Thank you. So what you can see here are the distributions of the differential energy flux in three different channels. So one in 10s keV range. The middle one shows keV range, and the right one shows the 100 EV range. So here we fix the BT at a certain magnitude, and we just try to see how the different energy, how the distributions in the different energy channels respond to the IMF clock angles. Here we show the due north condition, due east, due west, due south conditions. So for the KV range, so we didn't see very significance for the BY and BZ we didn't see very significant differences for the due east and due west IMF conditions. But for the 100 EV range, we see that the DSI peak actually are very different when the BY is positive and DY negative. For the BY positive case, the probably the peak locations is more toward to the afternoon sectors, while for the BY negative case, the peak is more or less more toward to the morning side. And also for also for the northward IMF, it seems that the peak density in the peak density in the 100 EV particles is more strong, even stronger than the BZ southward case, which is not seen in the KV particle. For the KV particles, it seems that when the BZ is southward, the differential energy flux is the strongest. So here, before looking for the impact of the soft electron precipitations on the thermosphere, so let me introduce another two components of Ashley model. So those are electric field components, which Ashley E and Ashley EVA, which also we use similar techniques, but the data is based on the on-drift measurement from the DMSP satellites during last solar cycles. So here the Ashley E and Ashley EVA provide consistent large mean electric field and electric field variability. So to investigate the impact of soft electron precipitations on the thermosphere, we have carried out the data comparisons during several intense geomagnetic storms. The model we are using still the Gitton model, and the data we are using are CHAMP aggressed neutral as the thermosphere measurements. For CHAMP, we also include the neutral wind measurements here. So here shows the geophysical conditions for the first storm. So which is a relatively weaker intense storm. So the DST the minimum CMH only reached about roughly across 100 minus 100 nanotesla, and the storm is triggered by a CR storm. But this storm, the storm also developed faster than the typical CR storm. So here, during this storm, two simulations has been carried out. The first storm, in the round one, so we directly use the spectrum from the Ashley A to drive the Gitton, and for the second one, so instead, we used the Maxwellian energy spectrum specified by the total energy flux and the characteristic energy calculated from the HAO spectrum. So which means in the second round, the soft electron precipitations is an underestimation. So except for the aurora precipitation specifications, other specifications for these two simulations are exactly the same. So both the Ashley E and EVA's component are used to drive Gitton, and the spectral resolution is 5 by 1/3 scale height. So what you can see on the right is the evolution of the CMH and the neutral density the neutral mass density along CHAMP and GRASS altitudes. So here to better show the evolutions of the neutral density, we show the percentage differences with respect to the quantum reference. So clearly, the results from round 1, as indicated by the red lines, are more consistent with the observations. But the differences between these two storms, two lines, are not very large. For the champ altitude, the difference is rough. The differences in terms of the percentage change is about 10%, and for the for the result along the grass altitude, the difference is about 16. So this is the result from the relatively weaker storm occurred in the solar maximum. And the second storm is a relatively stronger storm, which is a CME storm, occurred in the relatively moderate solar radiation conditions. So this storm is also characterized by a long-lasting magnetic cloud. Sorry, my computer is sort of frozen. Okay, so this is the geophysical conditions for the second storm. So which is the CME storm occurred in the moderate solar radiation conditions. So here is the result, similar for just following the same format shown in the first storm. So again, we have two simulations. One means the round 2 means the underestimation of soft electron precipitation. So clearly, for this storm, still the result from round 1 is closer to the observations, and the differences between round 1 and round 2 is more predominant. It's more significant than what you can see for the previous storm. So for the champ altitude, the difference is about 20%, and for the grass altitude, the differences can reach about 80%, 60%, which is definitely not negligible. So in addition to the neutral density, we also see how the neutral wind estimations can be changed due to the soft electron precipitations. So here we just show two examples where the neutral wind most effectively be changed by the soft electron precipitation. So what you can see is that the change mostly occurred near the aurora region, and for the first storm, the maximum change can be 100 meters per second, and for the second one, the maximum change is about 200 meters, which are definitely not negligible. And to see whether the changes near the aurora zone is always the case, we also carried out a statistical study to show how the neutral wind can be affected with and without the soft electron precipitation near the aurora zone. So this is the left one is showing the result from the 2002 storm, and the right one shows the result from 2003 storm. So both figures, as you can see, both figures, the result from the round 1, where the soft electron precipitation is better specified, has higher slopes, and the correlations between the observations and simulations is also high. So here is a summary for the second part. So first, we have developed a new input model, actually, which could have better advanced soft electron precipitation specifications. And also, when we improve the specifications of soft electron precipitation in the whole aurora zone, it seems that the thermosphere neutral density variations during geomagnetic storms and the high altitude neutral wind can be better estimated. So which may suggest that the soft electron precipitation may need to be better taken into account in GCMs. So the previous results are mainly from my PhD result. And here I'm going to briefly introduce what I'm currently doing. So I'm working on how to use more realistic forcing to drive GCMs. This is because although empirical models are very convenient to use, well, it also has its disadvantages are also standing out. So by using more realistic forcing to drive GCMs, it might also help to improve the jaw heating in GCMs. So what I proposed in my ASP proposal is try to use some AMI result, and I'm currently in the middle way of doing this result this plan. So I'm currently using the field current from ampere to drive the GITM. Currently is still using GITM to see how much the ions, how much it can, such technique can better reproduce some observed ionosphere thermosphere quantities, such as the ionosphere ion convection. And also, I'm currently trying to see how this method could reproduce the observed interhemispheric asymmetries of the ionosphere thermosphere system. So I'm currently collaborating with Gang, Astrid, and Lars for this project. So, and here is some preliminary result from my previous from this project. So here, what you can see here are comparisons of the cross-track ion drift along the several polar crossing of the DMSB F-17 satellites. So one thing promising is that by using the field current driving, it seems that the observed ion drift is better reproduced as compared with the simulation when only the empirical models is used as compared with the data. And there are also some inconsistencies which might be associated with the background electron precipitations. So currently, I'm currently only using the field current, the precipitations from my empirical models, which might not be that realistic. But in general, the result seems fine if the empirical model is used for this event. So this only shows several tracks, but the several conclusions can be made for other F-17 trajectories as well as F-16 and 18 satellites. So with that, I'll go. So this is the. So I'm going to summarize my presentation today. So, well, so in this presentation, I may address 3 directions that can improve the jaw heating specifications in GCMs. The first, it might be necessary to better specify small scale and mesoscale electric field and electric precipitation variabilities, as well as their correlations when empirical models are used. And also, soft electron precipitations may also deserve to be better into account. Finally, it might be worthwhile to using more realistic driving forces to drive GCMs. And with that, I'll stop here and happy to take any questions, comments, and suggestions. And looking forward to future collaborations. And thank you for your time.
Thank you. If anyone has any question, you can either speak up or type into the chat.
I have several questions about how you drove the simulations that you talked about in the first two parts. I guess it's mostly on your thesis work, but yeah. So, what was your electric field model?
Oh, the electric field model is from the imperial model I have built, the Ashley model.
So it's okay, yeah.
So
and so when does it change? So if the IMF and solar wind variables change, does the electric field change instantaneously in Ashley? Is that how that works?
yes, yeah, right. That's one of the purpose to develop both electric field and electric precipitation simultaneously.
Okay, and then for the precipitation, how is it driven? I mean, you showed plots of the electron precipitation, both the hard and soft, and so does the precipitation distribution and intensity vary as the IMF and solar wind vary for a storm? Is that how you're changing it?
Yeah, right. Yeah.
Okay. Okay, good. I'll stop there. I could ask more questions, but I'll let somebody else go in. Thank you, Qingyu.
Yeah, thank you. Yeah, we can talk offline. Yeah. Thank you. Thank you, Bill.
So there's a question from Dan Marsh, and would a simple first step be to replace the Maxwellian fit with a power law? And when integrated, what percentage of the total energy is missing?
So the total energy doesn't change very significantly if we just using the total energy doesn't very change between these two. If we only integrate about 1 keV and all as well as the whole spectrum. So if try to give a quantitative, probably less than 5 or 10%. That's my impression.
And the first part of his question, could you just replace the Maxwellian with a power law as a sort of simple way to do it?
Yes, I think maybe a double max with power law probably also a good way to do so. Yeah, also maybe a double Maxwellian may also help. Yeah, we for example we just do a Maxwellian for the KV and a Maxwellian for the soft part. Yeah, definitely there are more ways to address this question.
Okay, and then there's another question from Gong. In your Ashley model, how do you separate the large and small scale electric field? And she says, I'm sure you said it in your presentation, but she missed it.
Yeah, currently, so for the Ashley model, we didn't address the small scale one. So here the electric field variability is just the statistical representations of the difference between the observed one and the one provided by the Ashley E model. So currently, we didn't distinguish with small and large scale in an Ashley model, but that's the future direction we are going to pursue.
Okay. And then a question from Dong: how does a GITM deal with differential energy flux? Are there multiple energy channels?
Yes, so GITM has maybe 60 channels, maybe has very larger ranges than the DMSP range. So we do some interpolations and then use the Fang et al. 2010 ionization profile to calculate the ionizations associated with such spectrum, and then just combine with the solar induced ionizations to calculate the conductivity as well as the electron precipitation, electron density.
And Dan and Gong both say thank you.
Can I have a quick question?
Sure, let me.
Yeah, like slide 30, when you compare, yeah.
This one.
When you compare to Grace and the Champ, the comparison is done on orbit average density, or is a particular track, or this is what kind of density you compare?
Oh, I forgot to mention, this is the orbital average neutral mass density.
Okay, okay, so I missed that. Okay, okay.
Yeah, follow-on question. If you compare orbit by orbit, do you see how is the most effective, the increase of density at the high latitudes, or also in the mid-low latitude?
Yeah, it's actually both. It's almost global. Yeah, I have a backup. Yeah, this one. Yeah. So here we just show the percentage difference with respect to the between round 2 and round 1. So this is, so you can see the enhancement almost occurred maybe globally. This is northern hemisphere. This is southern hemisphere. This is for 2002 storm. This is for 2003 storm. For the 2003 storm, probably a larger enhancement occurred on the night side instead of the day side.
Yeah. Okay. Thanks.
I actually have a follow-up comment to Dan Marsh's question to you. And let me just say, this is not a criticism at all. I think we have to do what we can with what we've got, but until things improve in some ways. But it's a comment about the nature of the soft electron precipitation. Mm-hmm. And first of all, DMSP has essentially no pitch angle resolution. Right. And when this soft electron precipitation is measured with instruments that do have reasonably good pitch angle distribution, the soft electron distribution has two components. One is more or less isotropic and Maxwellian-like, and that component's mainly coming in the cusp region where you see that bright spot. For example, the third row, far right, that would probably be cusp precipitation coming from direct entry from the magnetosheath. Mm. Whereas the other component to the soft electron precipitation, what Pat Newell calls broadband electron precipitation arising from wave particle interactions, a lot of work that was done with the FAST satellite at higher altitude shows that that's highly anisotropic and very field aligned. That is, if you go at a particular energy and go away from V parallel equals 0 in the distribution function, the intensity falls off very rapidly. It's not clear how to model that. I think, doing it as you're doing is about as good as we can do at this point, but it's just a caveat in terms of how one interprets what the data really is telling us.
Yeah, right. Yeah, that's actually, one of my calls actually mentioned that. Yeah, the DMSP, the pitch angle resolution. Thank you for the comments. Yeah.
Are there any more questions? Yeah. Okay, it seems not. So why don't we conclude there, and thank you again.
All right, thank you for coming. Yeah.
Okay, thank you, Qingyu.